Students, that is the interhalogen compounds. Properties of interhalogen compounds. These are the types X, X bar, type and X, X3 bar, X, X5 bar, and X, X7 bar. Formula for the type X and X bar, where capital X is a larger size compared to X bar. Like that, there is example for Cn, F, Br, F, I, F, Br, Cn, I, Cl, I, Br. Examples for type this X bar. And Cn, F is a physical state and odor, physical state colorless gas. And Br, F is a pale brown color, pale brown gas. IF is a unstable, don't have any color, unstable. And PrCl is a gas. And ICl, it forms the two types of solids, and one is a ruby red solid. Ruby red solid, it is alpha form, and it is another one is brown red. Brown red, built up on these two other drops. And IBr is a black solids. This type of interhalogen compounds do not have any special. These are gases and some of the solids. And second type is X3 bar. Example Cl F3, Br F3, I F3, I Cl3. Here Cl F3 is a colorless gas and have bent T-shape. Bent T-shape. Why it has bent shape? Presence of a low pair of electrons. And BrF3 is a yellow-green liquid. Yellow-green liquid is a physical state and have the structure bent T-shape. T-shape means it is having a like a structure 1, 1, 1. These are the three F bonds, and its center is Br. Here 1 bromine, 3 F, and 1 is lone pair of electrons. Like the structure bent T shape structure or geometry. IF3 yellow powder, and it is also having the same T shape, bent T shape. ICl3 is an X3 bar type of interhalogen compound having the physical state orange solid, bent T shape. And the next type of interhalogen compound is X5 bar. Example ClF5, Br F5, I F5. ClF5 is a colorless gas and having the geometry distorted spiral pyramidal. Distorted spiral pyramidal. And BrF5 is a colorless liquid. IF5 is a colorless liquid having the same geometry distorted spiral pyramidal. And the last type of interhalogen compound is X7 bar, and it is example for this type IF7. One is a more larger size halogen is iodine, and lesser one is chlorine, IF7. It is a colorless gas and having the geometry pentagonal bipyramidal. The properties of interhalogens are compared with the group 17 halogens. Interhalogen compounds are more reactive than halogens. Interhalogen compounds are more reactive than halogens because interhalogen compounds are having covalent bonds and diamagnetic in nature. Why they are more reactive? Compared to X bar bond. In interhalogens, bond is weaker than XX bond. XX bond is present in halogens. X bar bond is present in interhalogens. XX bond is present in halogens. Here X bar bond is weaker than XX bond. So that X bar bond is easily broken compared to X bond in halogens. so that interhalogen compounds are more reactive compared to halogens, and it is important for 2 marks. And the next property, all the interhalogen compounds undergo hydrolysis. After addition of water to forms halide acids and hypohalides are respective. Different types forms of different types of halides undergo hydrolysis, giving the halide ion derived from the smaller halogen and a hypohalide. Hypohalide is formed when interhalogen compound taken X bar type. When we taken this type of interhalogen, if it is reacts with the X bar type, it is reacts with the water to form halide ion derived from the smaller hypohalide. When you take X bar type, if you take X3 bar type, in the place of hypohalide, it forms halides. In the type of XX5 bar forms halide. In case of X7 bar form perhalide, anion derived from the larger halogen. And let us continue the P block elements. Starts with the group 18 elements. Group 18 elements consists of 6 elements, namely helium, He, neon, Ne, argon, Ar, krypton, Kr, xenon, Ne, and last one, radon. All these are gases and commonly called rare gases. Rare gases means they have got very less quantity in the atmospheric air. They are all the gases and chemically inactive. The elements present in group 18 have their valency shell orbitals completely filled. Their valency shell orbitals are completely filled. Means they have electron configuration -2np6. Completely filled shell orbitals. Complete 8 electrons. Octet 6 plus 2. 8 electrons are completely filled their valency. Valency shell orbitals completely filled, therefore react with the very few elements only under certain conditions. So that group 18 elements are rare elements called as noble gases. And occurrence of group 18 elements are rare gases. All the noble gases except the radon, because radon is a radioactive in nature, except radon. All the noble gases, helium, neon, argon, krypton, xenon, are occur in the atmosphere. Atmosphere means atmospheric air. Their atmospheric abundance in dry air is nearly 1%, only 1% or nearly 1%, 0.95 something, nearly 1% by the volume, which among the 1%, among the nearly 0.99%, which argon is the major component. Argon is the major component. So that they are called rare gases. They are called very rare in the atmospheric air, called rare gases. Except helium, as I neon. Consequently, both helium and neon are found in minerals of radioactive minerals of radioactive origin. That is, example, pitch blended and monazite, cleveland, etc. The main commercial source of helium is natural gas. Helium is present in the natural gas, and helium also is one of the composition of sun. Xenon and radon are rarest elements of the group 18. And radon is obtained as a decay product by radioactive integration of radium 226. Disintegration of radium 226 converts into radon 222 plus helium. Atomic number 2, mass number 4. Containing group 18 elements, general characters. Group 18 elements are called noble gases and inert gases, rare gases, and having the completely filled electronic configuration NS2, NP6. General properties of group 18 elements are general properties of noble gases. General electronic configuration of group 18 elements is NS2, NP6, completely filled s orbitals, completely filled p orbitals. Completely filled s orbitals to NS2, completely filled p orbitals. 1, 2, 3 orbitals are present in P. P orbitals are completely filled. NP6. 1, 2, 3, 4, 5, 6. Except helium. For helium, it has only 2 electrons. 1 orbital, 2 electrons. NS2 for helium. And ionization enthalpy of noble gases, i.e., noble gases exhibit very high ionization enthalpy because of their stable electronic configuration, because there is completely filled orbitals. Because ionization enthalpy decreases down the road with the increase in atomic number. Helium, neon, argon, krypton, xenon, radon. Ionization enthalpy decreases down the road because the down the road increasing in atomic number. As the atomic number increases, ionization enthalpy also decreases. Next property, atomic radii. Atomic radii of the noble gases increases down the group with the increase in atomic number. Fourth property is electron gain enthalpy. Delta EZH. Delta is electron gain enthalpy. Noble gases have stable electron configuration, pretty we know that configuration, and they have no tendency to accept electron because they are completely filled. There is no tendency to accept electron and therefore have large positive values of electron gain enthalpy. And physical properties of noble gases. All the noble gases are monoatomic. Colorless, odorless, and tasteless gases. soluble in water. Sparingly soluble in water. It means half soluble in water and have very high, very low boiling point and melting points. Why they are low boiling point and melting points? Because interatomic bonds are very weak due to only weak dispersion forces, because all are gases. The next property is helium has melting point 4.2 Kelvin temperature of any known substances. So that it has an unusual property. It is a special property. It is an unusual property of diffusing through the most commonly used laboratory materials such as rubber, glasses, and plastics. Chemical properties of noble gases, group 18 elements. Noble gases are least reactive. Least reactive. It is called inertness. It is called inertness. Their inertness to chemical reactivity is attributed to the following reasons. For these three reasons, group 18 elements of noble gases act as a inertness, means least reactive. Why the least reactive of group 18 elements? Because of this reason. First reason is noble gases except the helium. Helium has in NH2 electron configuration generally, but after the helium, all the noble gases are completely filled NH2 NP6 electronic configuration in their valence shell. And second one, they have very high ionization enthalpy, and they have more positive electron gain enthalpy. Therefore, group 18 elements are noble gases. They can neither lose nor accept or gain electrons. Into the chemical properties of noble gases are group 18 elements. In 1962, Neil Bartlett, the scientist, prepared a red color compound, Xe plus PtF6. Compound name XePtF6, and it is prepared by mixing of PtF6 plus xenon, Xe. Xenon is the first noble gas, and the compounds of krypton are few, only few are, that is only one krypton dichloride. Krypton is available as a krypton dichloride. The compounds of radon have not been isolated yet, but identified radon dichloride by radio tracer technique. Radon dichloride as identified but not isolated. No true compounds of helium, neon, argon are not yet known. Helium, neon, argon compounds they are monatomic gases. Only two, xenon and krypton. Krypton, only one, that is krypton dichloride. So that we are going to study krypton compounds. In the form of xenon compounds, xenon fluoride compounds, xenon oxygen compounds. First, xenon fluoride compounds. XeF, xenon fluoride compounds. There are three types of xenon fluorides. One is XeF2, one is XeF4, XeF6. Xenon dichloride, xenon tetrafluoride, xenon hexafluoride. These are the three types of xenon fluoride compounds are prepared by the following methods. Xenon and fluorides are in that among these two, xenon in excess quantity is heated at a higher temperature 673 Kelvin temperature, low pressure 1 bar pressure. Then xenon plus fluoride converts into xenon difluoride. Xenon difluoride. The second one, xenon reacts with the fluorides, and xenon is 1 and 5 quantity of fluorides. 1:5 ratio of xenon and fluorides heated at 873 Kelvin, 7 bar pressure. Then it converts into xenon tetrafluoride. And third one, xenon and fluorides are taken in a 1:20 ratio. Higher excess quantity of fluorides taken in less quantity of xenon at a higher temperature 573 Kelvin, 60 to 70 bar pressure, more pressure compared to the temperature. Then converts into xenon hexafluorides, because 6 fluorides are xenon hexafluoride. The xenon hexafluoride also prepared by another method, that is xenon tetrafluoride. Xenon tetrafluoride is treated with the O2F2 dioxygen difluoride, O2F2, then converts into xenon hexafluoride plus O2. Preparation of xenon hexafluoride, there are two methods, 1 and 2. Among xenon difluoride, xenon tetrafluoride, xenon hexafluorides are colorless crystalline solids. Colorless crystalline solids. They are sublime readily at 298 Kelvin temperature. Sublime means they are directly converted solid to gases. Sublime readily at 298 Kelvin temperature. And xenon HCl2, HCl4, HCl6, xenon difluoride, tetrafluoride, hexafluorides are powerful fluorinating agents. They give fluorine to the given elements. They are powerful fluorinating agents, and they are hydrolyzed even by traces quantity of water. If we add a small quantity of traces quantity of water, then they are hydrolyzed. Addition of water, xenon difluoride converts into xenon plus hydrogen fluoride plus oxygen. They are hydrolyzed. This reaction is important. They use HCl2 plus water. Which compound is formed? This must be written for one more. And reacts with how xenon fluoride compounds reacts with the fluorine. They convert into cations. One fluorine in the xenon fluorides is transferred to the metal fluorides to form cation. See, xenon difluoride reacts with the PTFI, platinum pentafluoride, phosphorus pentafluoride. Then it is converts into XeF plus. One fluorine is donated to the phosphorus pentafluoride, converts into hexafluoride, anion. Like that, xenon tetrafluoride, it is a xenon fluoride compound, is reacts with the metal fluoride, that is SpF5. The one fluorine gives to the metal fluoride, that converts into SpF5, converts to SpF6. It is less than one fluorine. HCl4 converts to Hc, xenon trifluoride cation. Like the xenon hexafluoride. Xenon hexafluoride reacts with the metal fluorides Mf, where M is the sodium, potassium, rubidium, and cesium, group 1 element. Converts into metal cation plus xenon heptafluoride anions. And the next one is xenon oxygen compound. Next, xenon oxygen compounds. After the xenon fluoride compounds. Xenon fluoride compounds forms xenon difluoride, xenon tetrafluoride, xenon hexafluorides. Now, xenon oxygen compounds. Hydrolysis of xenon tetrafluoride and xenon hexafluoride with water gives xenon trioxide, XeO3. For example, 6, the reaction of xenon tetrafluoride with water. Xenon tetrafluoride reacts with 12 molecules of water to give 4 xenon plus 2 xenon trioxide, XeO3, plus 24 hydrogen fluoride, HF, 3 oxygen molecule. It uses xenon tetrafluoride reacts with the water to form xenon trioxide. Now, xenon hexafluoride, XeF6, xenon hexafluoride reacts with the 3 molecules of water to form xenon trioxide plus 6 hydrogen fluorides. It is a complete hydrolysis. Now, partial hydrolysis of xenon hexafluoride gives oxyfluorides. Partial hydrolysis of xenon hexafluoride reacts with the water to form xenon oxytetrafluoride. Xenon oxytetrafluorides. Oxyfluorides are formed when partial hydrolysis. Oxides are formed at a complete hydrolysis. Xenon F6, xenon hexafluoride reacts with the 2 molecules of water to form xenon difluoride plus 4 hydrogen fluoride. Xenon trioxide is a colorless explosive solid, and xenon oxytetrafluoride is a colorless volatile liquid. Easily volatile liquid. Now, the structures of the xenon fluoride compounds, xenon oxygen compounds. A. Xenon difluoride. These structures are used based on the VSEPR theory, valency shell electron pair repulsion theory. Based on that theory, they give the structures of xenon fluoride compounds, xenon oxygen compounds. Number 1, xenon difluorides. It is having 2 lone pairs, 1 and 2. 2 lone pairs and 2 bond pairs. So it is having the geometry linear, 180 degree. Linear geometry. And second one, xenon tetrafluoride. Xenon tetrafluoride, it is having 1, 2, 3, 4 bond pairs, electron pairs, and 2 lone pairs. So that it is having the geometry square planar geometry. And third one, xenon hexafluoride. Xenon hexafluoride, it is having 8 electron pairs. Among those 8, 7, 6, 1, 2, 3, 4, 5, 6 are bond pairs, 1 lone pair. 1 lone pair, 6 bond pairs. To form this geometry, discarded octahedron. If there is no lone pair of absence of lone pair of electrons, it is octahedron. But the presence of lone pair, it forms distorted octahedron. Xenon oxytetrafluoride. Xenon oxytetrafluoride, it is also 1, 2, 3, 4 bond pairs and 1 double bond with oxygen and 1 lone pair. So that it forms the structure and geometry square pyramidal geometry. Xenon trioxide, it has 3 bond pairs, 3 double bond with the oxygens and 1 lone pair. Forms geometry pyramidal. And the uses of noble gases. Uses of noble gases. First, helium. Helium is a non-flammable and light gas. Non-flammable because ಉರಿಯೋದಿಲ್ಲ ಜಾಸ್ತಿ. Non-flammable and light gas. ಹಗುರವಾಗಿರ್ತಕ್ಕಂಥ ಅನಿಲ. And hence it is used in filling balloons. Balloon ಅನ್ನು ಹೇಗೆ fill ಮಾಡಬೇಕಾಗಿತ್ತು ಅಂದ್ರೆ air filling balloons for meteorological observations. Meteorological observations ಅಂತಂದ್ರೆ ಹವಾಮಾನ ಇಲಾಖೆಗಳಲ್ಲಿ ಹವಾಮಾನ ನೋಡಬೇಕಾಗಿರುತ್ತೆ ಅಂತ ಸಮುದ್ರದ ದಾನ ಮಾಡ್ತಿರೋದು. And it is also used in gas cooled nuclear reactors. Gas cooled nuclear reactors. Nuclear reactors ಅಲ್ಲಿ heat ಜಾಸ್ತಿ ಪ್ರೊಡ್ಯೂಸ್ ಆಗ್ತಿರುತ್ತೆ. ಅಲ್ಲಿ ಅಂತ ಗ್ಯಾಸ್ ಅನ್ನ ಕೂಲ್ ಮಾಡಬೇಕಾಗುತ್ತೆ. ಗ್ಯಾಸ್ cooled nuclear reactor ಗಳಲ್ಲಿ helium ನ ಬಳಸ್ತಾರೆ. And liquid helium. Liquid helium is a gas. Now it is liquid helium boiling point 4.2 Kelvin. Liquid helium find use as a cryogenic agent. Cryogenic agent for carrying out various experiments at low temperatures. This is very important. ಕಡಿಮೆ ಟೆಂಪರೇಚರ್ ಇದ್ದಾಗ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಅನ್ನು ಮಾಡಬೇಕಾಗಿತ್ತಂದ್ರೆ ಹೀಲಿಯಂ ಲಿಕ್ವಿಡ್ ಹೀಲಿಯಂ ನ ಬಳಸ್ತಾರೆ. And it is used as a diluent for oxygen in modern diving apparatus. Modern diving apparatus ಅಂದ್ರೆ ಸಮುದ್ರದ ಒಳಗಡೆ ಹೋಗಬೇಕಾಗಿರೋ ಬಹಳಷ್ಟು ಸಮಯದಲ್ಲಿ ಆ ಡೈವಿಂಗ್ ನಲ್ಲಿ ಹೋಗಬೇಕಾದ್ರೆ ಏನ್ ಮಾಡ್ತಾರೆ, ಈ ಆಕ್ಸಿಜನ್ ಜೊತೆಗೆ ಹೀಲಿಯಂ ನು ಫಿಲ್ ಮಾಡಿರ್ತಕ್ಕಂಥ ಆಕ್ಸಿಜನ್ ಟ್ಯಾಂಕರ್ ಅನ್ನ ಕಟ್ಕೊಂಡು ಹೋಗಬೇಕಾಗುತ್ತೆ ಉಸಿರಾಟಕ್ಕೆ. ಆಕ್ಸಿಜನ್ ನೀರಿನಲ್ಲಿ ಏನಾಗಿರುತ್ತೆ, ಡೈಲ್ಯೂಟ್ ಆಕ್ಸಿಜನ್ ಇರುತ್ತೆ, ಡಿಸಾಲ್ವ್ಡ್ ಆಕ್ಸಿಜನ್ ಇರುತ್ತೆ. ಆ ಡಿಸಾಲ್ವ್ಡ್ ಆಕ್ಸಿಜನ್ ನಮಗೆ ಉಸಿರಾಟ ಮಾಡಕ್ ಆಗೋದಿಲ್ಲ. ಹಾಗಾಗಿ ಆಕ್ಸಿಜನ್ ಪ್ಲಸ್ ಹೀಲಿಯಂ ಇರತಕ್ಕಂಥ ಸಿಲಿಂಡರ್ ಅನ್ನ ತಗೊಂಡು ಹೋಗಬೇಕಾಗುತ್ತೆ. ಏನ್ ಮಾಡುತ್ತೆ, ಡೈಲ್ಯೂಟ್ ಆಕ್ಸಿಜನ್ ಇನ್ ಮಾಡರ್ನ್ ಅಪಾರಟಸ್ ಬಿಕಾಸ್ ಆಫ್ ದಿಸ್ helium plus oxygen. It's a very low solubility in blood. It's very important. ಏನ್ ಮಾಡುತ್ತೆ, ಕಡಿಮೆ ಸಾಲ್ಯುಬಲ್ ಆಗೋ ತರ ನೋಡ್ಕೊಳ್ಳುತ್ತೆ. ಲೋ ಸಾಲ್ಯುಬಿಲಿಟಿ ಇನ್ ಬ್ಲಡ್. ಅಕಸ್ಮಾತ್ ಇಲ್ಲ ಅಂದ್ರೆ ಏನಾಗುತ್ತೆ, ಇಲ್ಲ ಅಂದ್ರೆ ಉಸಿರಾಟಕ್ಕೆ ತೊಂದರೆ ಆಗುತ್ತೆ. ಅಂಡ್ ನಿಯಾನ್, ಯೂಸಸ್ ಆಫ್ ನಿಯಾನ್. ನಿಯಾನ್ ಈಸ್ ಯೂಸ್ಡ್ ಇನ್ ಡಿಸ್ಚಾರ್ಜ್ ಟ್ಯೂಬ್ಸ್. Used in discharge tubes and fluorescent bulbs for advertisement display purposes. ಜಾಹೀರಾತು ಫಲಕಗಳಲ್ಲಿ ಕೆಲವು ಬಣ್ಣ ಬಣ್ಣದ ಬೆಳಕನ್ನ ಬಂದಿರುತ್ತೆ. ಆ ಬೆಳಕಿನ ಕಾರಣ ಇದನ್ನ ಫಿಲ್ ಮಾಡಿರ್ತಾರೆ ನಿಯಾನ್ ಫಾರ್ ಅಡ್ವರ್ಟೈಸ್ಮೆಂಟ್ ಡಿಸ್ಪ್ಲೇ ಪರ್ಪಸ್. And neon also used in bulbs are used in the botanical gardens. Botanical gardens and greenhouses. Argon uses. Argon is used mainly to provide inert atmosphere in high temperature for metallurgical process. Metals or metal plus metal alloys na ಮಾಡಬೇಕಾಗಿರುತ್ತ. ಆ alloy ಪ್ರಿಪೇರ್ ಮಾಡಬೇಕಾಗಿತ್ತು ಮೆಟಲರ್ಜಿಕಲ್ ಪ್ರಾಸೆಸ್ ಮಾಡಬೇಕಾಗಿತ್ತು ಅಂತಂದ್ರೆ ಆ ಸಮಯದಲ್ಲಿ ಇನರ್ಟ್ ಅಟ್ಮಾಸ್ಫಿಯರ್ ಬೇಕು, ನಿರ್ವಾತ ಪ್ರದೇಶ, ಜಾಸ್ತಿ ರಿಯಾಕ್ಟಿವ್ ಅನ್ರಿಯಾಕ್ಟಿವ್ ಅಟ್ಮಾಸ್ಫಿಯರ್ ಬೇಕು ಅಂತಂದಾಗ ಅಲ್ಲಿ ಅರ್ಗಾನ್ ಅನ್ನ ಯೂಸ್ ಮಾಡ್ತಾರೆ, ಹೈ ಟೆಂಪರೇಚರ್ ಇದೆ. ಅಂಡ್ ಅರ್ಗಾನ್ ಆಲ್ಸೋ ಯೂಸ್ಡ್ ಫಾರ್ ಫಿಲ್ಲಿಂಗ್ ಎಲೆಕ್ಟ್ರಿಕಲ್ ಬಲ್ಬ್ಸ್. ಎಲೆಕ್ಟ್ರಿಕಲ್ ಬಲ್ಬ್ ಒಳಗೆ ಟಂಗ್ಸ್ಟನ್ ಇರುತ್ತೆ. ಆ ಟಂಗ್ಸ್ಟನ್ ಬಿಟ್ಟು ಅದನ್ನ ಇದಾಗಬೇಕಂತ ಏನ್ ಮಾಡಿರ್ತಾರೆ, ಅರ್ಗಾನ್ ಅನ್ನ ತುಂಬಿರ್ತಾರೆ. ಬಲ್ಬ್ ಅಲ್ಲಿ ಇರ್ತಕ್ಕಂಥ ಗ್ಯಾಸ್ ಅರ್ಗಾನ್. Used for filling electrical bulbs. Which gas is present in electrical bulb? Argon. Second uses of argon. It is also used in the laboratory for handling substances that are air sensitive. Air sensitive ಇರತಕ್ಕಂತ ಸಬ್ಸ್ಟೆನ್ಸ್ ನ ಮೆಜರ್ ಮಾಡಬೇಕಾಗಿತ್ತು ಅಂತಂದಾಗ argon ಅನ್ನ ಬಳಸ್ತಾರೆ. And xenon and krypton. Krypton and xenon, there is no significant uses, but sometimes they are used in the light bulbs designed for special purpose.